Alright, silly people, here's the situation. Griffiths wants us to prove that the components of a vector are unique um, with respect to a given basis. So what I've written here is the vector alpha. Um, in the same basis as in both equations, the basis is just vectors 1, 2, on to vectors n. Um, but you'll notice that uh, I've written different components to the vectors for either one. The one up top is A's all the way down, and then the other one is B's all the way down. And we're assuming that A sub I is not equal to B sub I for now. But what we can do here is we can take both of the equations and then subtract the second equation from the first. So on the left-hand side, you would get the vector alpha minus the vector alpha. On the right-hand side, you would have a1 minus b1 times the vector 1 plus a2 minus b2 times the vector 2, and on until an minus bn times the vector n. We can actually carry out the subtraction on the left-hand side because that should be 0. We can use that fact. But the right-hand side we can't do anything with because we assume that AI is not equal to BI. But we can go component by component and write out the null vector in its entirety because it is the null vector. So it would be 0, 1 plus 0, 2 plus dot 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 plus 0 n. And then we can go component by component comparing it to the right hand side, and we would get a1 minus b1 equals 0, a2 minus b2 equals 0, an minus bn equals 0. And you can solve all of those equations for the a's, and you'll find that every a is equal to the b. So since AI is equal to BI, that's a contradiction to our assumption. So by that fact, we have proven that the components of a vector are unique to a given basis. All right.